Can you record to the cloud? Oh yeah, there you go. Perfect. Sorry to interrupt, Sonia. Please go ahead.
Sonia, you're still muted.
I'm still muted. I just realized that. Yes. Doesn't matter at all. So my name is Sonja Klingert. I'm from University of Mannheim, and I've been working in data center demand response and other issues as establishing energy communities, for instance. So today I see that the recording has started. Today we have 1 hour with 2 full recorded papers, as Paul said. So that means that potentially we have 7 minutes of discussion for each of the papers. Is there by chance any of the authors present? I haven't checked the list.
Hi, I'm Russell. I'm the author for the first paper.
Hi, hey, that's great. So it must be in the middle of the night for you. Okay, then I will just introduce the first paper and the first author of the paper. The first paper is on online peak-aware energy scheduling with Untrusted Advice. It's been nominating for the Best Paper Award, and it's presented as recorded by Russell Lee. And Russell, you're a PhD student at UMass Amherst in the College of Information and Computer Science. You're advised by Mohammad Hajiesmaili. I hope this is spelled correct. This is pronounced correctly. And your interests are in online optimization and data center optimization. Before UMass, you received your bachelor in the mathematical sciences from Carnegie Mellon University. So, Paul, would you please start the recording now?
Hi there, my name is Russell Lee and I am a graduate student at UMass Amherst. Today I am presenting online peak-aware energy scheduling with Untrusted Advice. This is a joint work together in Jessica and Zhenhua at Stony Brook, Mohammad at UMass, Jian at Binghamton, and Ramesh at UMass and Akamai. In the energy scheduling landscape, a large-scale energy customer may satisfy their energy needs from multiple different sources. Minimizing the cost of energy scheduling is of significant interest to data centers since energy consumption can comprise more than 30% of the total operating costs for data centers at locations such as Google and Microsoft. We consider the scenario where a portion of the electricity demand is covered by renewable energy sources such as wind and solar power, and the remaining net demand may be covered by local generators or an external grid. The main element of the energy scheduling problem is then allocating between these two energy sources. This problem is made challenging by two main factors, however. First, the electricity bill is based on a peak charging scheme where a significant cost is incurred based on the maximum electricity demand drawn over the billing period from the external grid. In an ideal world, data centers would be able to accurately anticipate their future electricity demand over the whole billing period in order to minimize this peak-based charge. However, the future demand is difficult to predict in practice due to multiple different factors. For example, a data center serving videos to users can experience a flash crowd upon serving a popular video release, driving electricity demands up suddenly. In another case, a geographical load balancer can move user demand in or out of the data center, which subsequently also changes the electricity demand unexpectedly. And even if we relax this assumption and allow electricity demand to be somewhat predictable, unpredictable renewable generation results in inherently unpredictable net demand. We consider a 1-week period of electricity demand for Akamai data centers, shown as a blue curve. In the New York City data center, the demand is roughly diurnal, with demand rising during the day and falling at night. However, the renewable energy generation plotted as a red curve is comparatively unpredictable. As a result, the net demand of subtracting renewable generation from the electricity demand is also comparatively unpredictable. This effect of uncertain renewable generation is even more pronounced in the Rochester data center, which experiences a relatively flat electricity demand, but it has a highly unpredictable net demand after renewable generation. The price of electricity is also unpredictable over different times of the day. Here, we consider the spot price of electricity from the New York energy market over 3 different days in August. Notably, the prices on August 2nd plotted in red do not experience any spikes in pricing, while August 1st and August 3rd plotted in blue and green, they experience spikes around 3 to 4 times the regular price between 2 and 4 p.m. There are several different approaches to this energy scheduling problem, and as a motivating example, we highlight the performance of 3 different algorithms over 100 trials, and this is done at 200 different data center locations. The metric used for evaluation is the normalized cost, where a lower normalized cost is better. Also, by reporting the 99th percentile, we report the worst case performance over the 100 trials at each data center. Here, the first algorithm considered is a pessimistic pure online algorithm. This algorithm deals with the uncertainty of future inputs by making no assumptions on what is coming in the future, and it acts solely on energy demand and prices that it has actually observed so far. It optimizes for worst-case performance, with the maximum normalized cost being no more than about 1.42. The second algorithm considered is an optimistic, purely prediction-based algorithm. To deal with the uncertainty of future inputs, this algorithm optimistically trusts a set of predictions on future inputs. Its worst-case performance suffers as a result, as its heavy right tail indicates that around 5% of instances had normalized cost over 1.5. On the other hand, its average case performance is noticeably better, with around 90% of instances having a lower normalized cost than the pessimistic algorithm. Finally, the last algorithm we consider is an online algorithm using machine learning advice. This is the algorithmic approach that we will consider in this work, and it achieves improved performance in both regimes of worst case and average case performance. This algorithm, it also receives a prediction on future input. However, it treats this prediction as a piece of advice that it can decide how much to utilize, spanning between fully ignoring the advice and fully utilizing the advice. Formally, the peak-aware energy scheduling problem is this following minimization problem. And actually, this problem was first presented in eEnergy 2015, but today we're going to be solving it with this novel framework of untrusted advice. First, the volume charge from the external grid is based on a time-varying spot energy prices, P of T. Next, the peak charge from the external grid is based on the maximum usage over the billing period times P sub M. And finally, the volume charge from the local generator is based on the constant generator cost P sub G. The demand constraint ensures that the total energy demand assigned to the grid or local generator must meet the time-varying electricity demand E of T, while the capacity constraint limits the maximum usage of the local generator. And for this problem, the demand and price are only known for the current time slot. If they were known, then standard linear optimization techniques can be used to solve this problem quickly and efficiently. However, since they are unknown for future slots, we use a class of algorithms called online algorithms to solve this problem. In the setting of online algorithms, the inputs arrive sequentially, and the online algorithm must take an action at each step without knowing future inputs. Since future inputs are unknown, it is very difficult for the algorithm to have optimal performance over the whole time horizon. To analyze the performance of online algorithms, we compare the costs against the optimal offline algorithm, which knows the entire sequence of inputs. This metric is known as a competitive ratio. Since the cost of the online algorithm is always at least the cost of the offline optimal algorithm, this ratio is always at least 1. And the lower the competitive ratio, the better it is. However, the downside of this method of analysis is that it measures the worst case ratio over all possible instances. However, worst case instances are kind of rare in practice, and we want to be able to utilize some sort of predictions about our future inputs in order to improve our performance in the average case. This leads to the following extension: online algorithms with untrusted advice. This extended framework for online algorithms is a rather recent work, and it utilizes a prediction on future inputs. This prediction might be correct or incorrect, while the true value of the inputs are still revealed sequentially in an online manner. And in this setting, competitive analysis of online algorithms must be done in two cases, whether the prediction is incorrect or correct. These online algorithms with untrusted advice are parameterized by lambda, which determines the level of trust in the advice. It is possible to set lambda such that the algorithm completely ignores the advice, completely trusts the advice, or somewhere in between these two extremes. In the first case, we use robustness to characterize the competitive ratio when the error of the advice is unbounded, or in other words, we make no assumptions about the accuracy of the advice. We say an algorithm is alpha robust if the cost of the online algorithm parameterized by lambda is at most alpha times the cost of the offline optimal algorithm for any error level epsilon. In the second case, we use consistency to characterize the competitive ratio when the advice is fully accurate. We say an online algorithm is gamma consistent if the cost of the online algorithm parameterized by lambda is at most gamma times the cost of the offline optimal algorithm with error equal to 0. Since we have these two criteria, robustness and consistency for competitive analysis, it is useful to consider the Pareto optimality of online algorithms. Optimal pairs of robustness and consistency lie on the Pareto frontier, where no other pair of robustness and consistency is smaller in both dimensions. And in fact, we show that our proposed deterministic algorithm for the peak-aware energy scheduling problem is Pareto optimal in the sense that our algorithm defines the Pareto frontier itself. As a warm-up, let's take a look at the ski rental problem. The basic ski rental problem is a classic problem in online algorithms. In this problem, a skier wishes to ski during the winter ski season, but does not know the actual length of the ski season. Every day, the skier arrives at the ski shop and can either rent the skis for a unit price or pay a one-time price of B to buy the skis entirely. The risk of renting skis continually is that the skiing season may extend for a long time, at which point renting becomes a poor choice, especially if the ski season extends beyond B number of days. On the other hand, the risk of buying immediately is that the skiing season may be very short, especially if the ski season is less than B number of days. To manage the trade-off of both decisions, the skier utilizes what is called a break-even point, which is the point at which the cost of renting breaks even with the cost of buying. With unit price renting and cost B buying, this point is a Bth day. The best deterministic algorithm without using predictions has a competitive ratio of 2, which has a strategy of renting until the break-even point B, which is the day it will buy the skis. Now, we consider the setting where the skier receives a prediction on the number of skiing days, where Y is a predicted number of skiing days. Y may or may not be correct, and it is up to the skier to decide how to utilize this advice Y. The best deterministic algorithm compares this advice against the break-even point to determine if the prediction is suggesting a long or short skiing season. The hyperparameter lambda determines the trust level by adjusting when to buy the skis. It is useful to examine behavior at the endpoints of lambda. Setting lambda equal to 0 will cause the skier to buy immediately if advise a skiing season longer than B, or it will rent continually if advise a skiing season shorter than B. Setting lambda equal to 1 will essentially ignore the advice and revert to the pure online algorithm of buying on the Bth day. This algorithm is 1 plus 1 over lambda robust and 1 plus lambda consistent. The important takeaway from these expressions for robustness and consistency is that it is possible for this algorithm to recover optimal competitive ratios in the sense that it is possible to be optimally 2 robust with lambda equal to 1 and 1 competitive with lambda equal to 0. Now, we consider our peak-aware energy scheduling problem with untrusted advice. Our problem does share some similarities with the ski rental problem. Primarily, there is some sense of a rent or buy nature in the choice between using the local generator and the external grid. Once we do commit to using a unit of electricity from the external grid, there is a one-time fee of the peak charge P sub m, as long as we don't exceed using more than 1 unit in any of the time slots in the future. Using the local generator can be cheap for the short term or for small demand traces, but there is a certain point where paying the peak charge P sub m to use the external grid is worthwhile. Specifically, there is a break-even point where solely utilizing the local generator breaks even with using the external grid. The algorithm receives a prediction sigma hat on this break-even point, which is provided either through a machine learning model or calculated through predictions on future inputs of demand and price. However, we face additional challenges compared to the ski rental problem. The energy demand and electricity prices, EFT and PFT, are time varying. From this, the cost of procuring energy at each time step is certainly not a known constant, unlike ski rental, where the cost at each step is just either 1 or B. Our proposed algorithm utilizes the advice sigma hat as follows. First, it compares sigma hat against 1. If sigma hat is greater than 1, the prediction indicates that using the grid for the whole billing period is cheaper. And in the other case, if sigma hat is less than or equal to 1, using the local generator for the whole period is cheaper. The algorithm picks a switching point S depending on the device and parameterized by trust level lambda. The best online algorithm without advice switches at S equals to 1, and it is also 2 minus beta competitive, where beta is a problem-specific parameter between 0 and 1. After this, the algorithm itself will behave in a rent-then-buy manner. It uses the local generator first and switches to the grid once a threshold based on the switching point S is reached. One advantage of our algorithm is that the trust parameter is naturally interpretable. It will fully trust the advice if lambda equals to 0, but if lambda is equal to 1, it essentially ignores the device and acts as a pure online algorithm. Intermediate values of lambda are also easily interpretable. For example, setting lambda equal to 0.5 will either increase the switching threshold by a factor of 2 or divide it by a factor of 2. Finally, our algorithm is 1 plus 1 minus beta divided by lambda robust and 1 plus lambda times 1 minus beta consistent. And there are 2 key points about this result. First, this can recover optimal competitive ratios by setting lambda equal to 1, resulting in 2 minus beta robustness, and by setting lambda equal to 0, resulting in 1 consistency. Second, we prove that this robustness and consistency defines the Pareto frontier, where no other deterministic algorithm can improve on our algorithm in both dimensions. Our full work also includes some additional results, where we propose a randomized algorithm that performs better than this deterministic algorithm in expectation. Furthermore, we provide some competitive analysis for the setting where we are provided a prediction sigma hat that varies over time. And to evaluate our theoretical contributions, we conducted experiments using energy demand traces from 338 Akamai data centers. For the renewable energy traces, we used an open data set on wind turbine renewable generation data from the National Renewable Energy Laboratory. And our energy prices are also from an open data set from the 2018 New York electricity market. We assume that the data centers are billed every month and the demand and prices are updated every 5 minutes. In our experiments, we evaluate the effect of several different problem parameters, and today we'll highlight the effect of 2 such parameters. The first one is the magnitude of the peak charge P sub m, which varies between 1 times and 20 times the regular value. The normalized cost is the competitive ratio with respect to the offline optimal algorithm, and it is reported as an average over 30 instances. First, this orange curve is the base online algorithm which does not utilize predictions. The purple curve is the algorithm which finds the best possible trust parameter lambda in an offline manner, so this algorithm has the best attainable performance using advice. This blue curve has a static trust parameter of lambda equal to 0.5, while the yellow curve uses a naive parameter selection method of selecting the best lambda in the previous 5-minute time slot. Now first, from these figures, notice that the overall pattern of increasing then decreasing normalized costs for all the algorithms. This indicates that the peak price P sub n makes the problem quite easy for extreme values. This makes sense because if the peak charge is very small, it is quickly apparent that the best strategy is to utilize the external grid. While if the peak charge is prohibitively large, the best strategy is to avoid the grid entirely. The orange curve for the pure online algorithm has a worse performance overall, which makes sense given that it is optimized for worst case performance, and we are reporting an empirical average performance. The trust-based algorithms all perform noticeably better than this one. And in particular, the naive parameter selection algorithm plotted by the yellow curve is as good as the best offline optimal parameter selection algorithm plotted by the purple curve for peak price scaled greater than 5 times. In our second plot, we consider the effect of local generator capacity, denoted by rho, scaled between 0 to 100% of the maximum energy demand. For evaluation, we report the cost reduction compared to a baseline which does not have access to local generation at all. As the local generation capacity increases, the cost reduction of all algorithms steadily increases until the capacity level reaches 40%. From 40% onwards, the cost reduction of algorithms with lambda equal to 0.5 and the pure online algorithm in red and orange begin to decrease. In particular, the pure online algorithm degrades drastically by the time rho reaches 100%. This can be interpreted as making use of the additional local generation capacity incorrectly, when in fact these algorithms were better off limiting their local generator use at 40%. On the other hand, the cost reduction of the algorithm with better trust parameter selection, which is the yellow curve, continues to experience cost reduction throughout increasing generator capacity. Once again, it achieves performance very close to the optimal offline parameter selection algorithm. Overall, in these two experiments, the naive parameter selection algorithm is practically almost as good as the best offline parameter selection algorithm. Furthermore, these experiments highlight the importance of carefully selecting the trust parameter lambda. Setting lambda equal to 0.5 will perform comparatively poorly compared to the naive parameter selection method. In conclusion, we applied the recent framework of online algorithms with untrusted advice to the peak-aware energy scheduling problem. For future direction, the Pareto optimality of a randomized algorithm is still unanswered. Our randomized algorithm improves on the deterministic algorithm, but it is unclear whether it is Pareto optimal. As for a starting point, there is a recent result on Pareto optimality of a randomized algorithm for ski rental with untrusted advice. And this is a fairly good starting point for investigating this. And that's it for our talk, and thanks for listening.
Okay, thank you for this awesome talk, Russell, and it's great that you're here. So we have 7 minutes for Q&A, and I see, meanwhile, 3 questions already in the chat. The first is from Hartmut Schmeck. Hartmut, do you want to pose the question yourself?
Yes, I would like to do that. So thank you very much, Russell, for this interesting talk. You're addressing a very valid problem and an important problem, but somehow I'm puzzled by the approach you take in your algorithm. Like you talk about reducing the peak or being peak aware, but when you are designing your algorithm, you are just deciding whether to switch or at what point to switch from local generation to external generation, to getting the power from the grid. So in that decision, you're not considering really whether there are peaks or whether it is reasonable at that point at all to use the local generation, which would have been able to reduce a peak at a later time. So a much more reasonable approach would be to determine thresholds, because at some point you know that certain demands will never be a peak. And so for those demands, you can easily provide them with local generation. And there has been another talk where exactly that approach has been taken. And I would be interested to hear what you think about this.
Hi, yeah, thanks for the question. Yeah, so in our approach, we don't explicitly try to reduce the incoming peak demand. We just assume that it's incoming and there's nothing we can do to change it. But yes, in this other work, they took this approach of using energy storage to reduce the peak demand. But although we do consider the peak demand in the sense that there is a point where switching from the local generator to the external grid is advantageous. In particular, we have this assumption that purchasing electricity from the grid is the volume pricing is cheaper than using the local generator. However, the peak charge is quite large. So depending on how large the incoming demand is and how expensive the peak charge is, there is a certain break-even point where you need to switch from the local generator to the external grid.
But the difference to the other paper is not just that you are using a local generator and they are using storage. Storage can also be seen, and it's only used there as local generation and nothing else. So that's the same prerequisite, but their algorithmic approach is very different, and they are using thresholds. They are using exactly the information they have from observing what has happened so far, and that can improve their algorithm.
A short answer, please, because there are also others who want to discuss this, so you can probably take this offline. Mohammad, you wanted to say something, yes?
Yeah, I can just provide a very quick also follow-up answer. I think what you are talking about, it's valid, but it fully relies on prediction that, okay, so if you know that you do have this minimum base load over the entire billing cycle, of course, you can just simply use this one as a threshold and just directly satisfy this one from the grid, because you know how you have to eventually pay this base load, the peak demand for this base load. And so I would say this is again based on the prediction that you do have. But our approach is that, okay, so we do not rely even in the first design on predictions. So it could be, I mean, if you think that you do have this prediction.
We should continue that discussion later on, I think.
Yeah, I mean, that's the whole point that I'd like to mention here is that the type of worst case analysis that we are considering here, we have to ignore this base load prediction somehow.
Okay, thank you very much, Mohammad. You can really take this discussion offline. The second question that I saw in the chat was from Keshav, but I think it might have been already answered. Keshav, have you seen the answer in the chat about?
I didn't see that. Okay, that's fine then.
Close your question quickly, and maybe one of the authors can.
I think the answer just says that this is possible in practice. So all I was saying was that if you know that your advice is good, then you can make lambda smaller, and if it's bad, you can make it larger. So you can tune it, and that in other work I've done in the past, this has been proved very helpful.
Yes, I think this is something that we can do for sure, and I think we do have some experiments investigating the impact of changing lambda.
Okay, all right, thank you.
Okay, thanks. Final question from Herman.
Hi, thanks. Just a simple question. You said that the naive approach fares pretty well in the end to extend the lambda, the best previous lambdas. So can you give, let's say, the assumption under which this holds, or does this hold generally?
So the naive approach is that the prediction is just is based on the best parameter in the previous 5-minute time slot. And so our intuition is that this means that in our data traces, the problem parameters are not changing drastically between 5-minute to 5-minute time slots. So we believe that perhaps in some setting where there are drastic changes in between different 5-minute time slots, then perhaps this naive parameter selection may suffer in performance.
But you haven't formalized this somehow. So this is quite informal statement of the assumptions then, right?
Yeah.
Okay. So then thank you very much for the questions and answers for this session. And I would like to move on to the second talk then.